We are on AP Review, FRQ topic number 5, differential equations. And I'd just like to begin with a brief review of how to solve a differential equation. So let's say we're given this differential equation. Our phrase that we like to use on these to solve a differential equation, you separate and then integrate. So we want to use algebra to move all of our y's on the left hand side with the dy, and we're going to multiply both sides by that dx, and so we're going to have all the y's on the left and all the x's on the right. So separating, and then after that we will integrate both sides. So remember that you can only use algebra, you can only use correct algebra to move this y squared over. So to move this y squared to this side, we need to divide both sides by y squared, right? So we're dividing both sides by y squared, which is the same thing as multiplying by 1 over y squared. And then we're going to multiply both sides by that dx. So we're going to have 1 over y squared dy, or you can write that as dy over y squared, is equal to 3x dx. Alright, so at this point we have it separated because all of our y terms are over here and all of our x terms are over here. We could have moved the 3 with the y squared. We could have had 1 over 3y squared. I always find it easier to leave any constant possible over here on this side. It's easier because we're going to end up solving for y anyway. So we might as well leave anything extra on this side because we're going to have to solve for y here anyway. So we're going to integrate both sides now. This integral is with respect to y and this integral is with respect to x. And the antiderivative of 1 over y squared is negative 1 over y. And if you don't see that readily, think of 1 over y squared as y to the negative 2, raise the power by 1, and then divide by that power, right? So negative 1 over y. This would have a plus c with it. I'm going to combine this constant of integration with the constant of integration I get over on this side and make it a single plus c on the right hand side. The antiderivative of 3x is 3 over 2x squared, and here's our constant of integration. Don't forget your constant of integration here. Okay, at this point I would look at the problem and ask myself, okay, did they give me a way to find c? If they gave me a way to find c, they would have said here, given that maybe y at, let's say, 2 is equal to 1. So they gave me an initial condition so that this general equation I can get a specific solution for. So I'm going, if they do give you an initial condition, once you integrate, look at your equation. Ask yourself, is this a good place to put in 2 in for x and 1 in for y? Is this a good place? If it is a good place, go ahead and do it. If it's not a good place, do another step. Maybe multiply both sides by a negative 1, or use our property to solve this for y. In this case, though, this seems like a fairly reasonable place to put 2 in for x and 1 in for y. It'll be easy to put 1 in for y. I'll just get a negative 1 here. And if I put 2 in for x here, I can reduce with that 2. So it's looking kind of pleasant to do. So I'm going to go ahead and do that. So I'm telling AP what I'm doing. I'm plugging in the point 2, 1. So I'm going to get negative 1 on the left-hand side is equal to 3/2 of 4. The 4 and the 2 are going to reduce, and I'll have 3 times 2. So c here will be negative 7. And so I will have negative 1 over y. I come back up here and put negative 7 in for c. And now I'm going to solve this for y. So multiply both sides by a negative 1. And then to solve this for y, I'm going to multiply both sides by y and divide both sides by this entire side. So I will get y is equal to 1 over that entire side. Not 1 over each term. That's not how it works. That's not good algebra. This is how it works. 1 over the entire side. So this would be our safe stop spot. And if we wanted to, we could multiply both sides by that 2 over 2. So we would get 2 over negative 3x squared plus 14. And that's fine too. So that is just a real brief review of how to solve a differential equation. I wanted to take the time to do that because these, if they appear as an FRQ question, solving a differential equation is always worth a lot of points. So you always want to make sure that you get all of those points for that. Take your time, solve that right. Okay. So now I'm moving to our little worksheet packet, and I'm going to begin by doing the problem from 2017. This was number 4, which was without a calculator. And let's read through this. It says, at time 0, a boiled potato is taken from a pot on a stove and left to cool in a kitchen. The internal temperature of the potato is 91 degrees Celsius at time 0. Here is an initial condition. At time 0, the temperature is 91 degrees. Okay? And the internal temperature of the potato is greater than 27 degrees for all times. So maybe 27 degrees is the room temperature, something like that. But the potato is always greater than 27 degrees. The internal temperature of the potato at time t minutes can be modeled by the function h. So h is the temperature of the potato. So this initial condition here gives me h at time 0 is 91 degrees Celsius. So h satisfies this differential equation. dh dt is negative 1/4 the h minus 27, where h of t is measured in degrees Celsius, and that's what I just wrote up there. H of 0 is 91. Okay, so part A. Write an equation for the line tangent to the graph of h at time 0. Let's do that first. So we want an equation of a line tangent. So the equation of any line, I need a point and I need a slope. So the point is going to be h at 0. And h at 0 is given to us. It's 91. So they gave us the point. Now for the slope. The slope is h prime at 0. We need to find h prime of t first, right? Well, they gave us h prime of t. So I can go ahead and put h prime of 0 in, right? Because this is dh dt, that is h prime. So we can plug 0, we want to plug 0 in for the time, right? We're plugging 0 in for the time. So let me write that like I originally wanted to. H prime of t is negative 1/4 h minus 27. So at time 0, h prime, at time 0, h is 91. So I'm going to plug in 91 in for h. The other way to write that, in hindsight, I could have written it like this. dh dt at time equals 0, h equals 91. Could have written it like that for that slope. So this is our slope at time 0. So the equation of the tangent line, I guess that would be the slope. The equation of the tangent line would be y minus the y value, the 91, is equal to the slope times x minus the x value. So that is the equation of the line tangent, and I could just leave it like that. Just leave it like that. Now we want to use this equation to approximate the temperature of the potato at time 3. So we want to use this to approximate h at 3, right? So y is our h. So I'm going to change this to h. So h is equal to 91 minus that 1/4, 91 minus 27 times t. X is representing our time. So h at time 3 would be 91 minus that times 3. And I could stop right there. They didn't ask me for units, so I'm not going to give them units, but that would be in degrees Celsius. Okay. Part B. Use the second derivative of h with respect to t to determine whether your answer in Part A is an overestimate or underestimate of the internal temperature. The second derivative, remember, that determines concavity. So h is going to have some, it's a curve, right? H is some kind of curve. And the concavity of that curve will help us determine if a tangent line will be above the curve or below the curve. If we have a concave down curve, then the tangent line would be above the curve. So this would be an overestimate. If we have a concave up curve, then the tangent line would fall below the curve, and so our tangent line approximation would be an underestimate. So here we go. We're going to find the second derivative. So I'm going to write the first derivative. I'm just copying down this equation. And we're finding the second derivative, so we're going to take the derivative of both sides with respect to t. Okay, so this will be the second derivative of h with respect to t. Now we're taking the derivative of this with respect to t, so implicit, right? This is if we distributed the negative 1/4. We would have negative 1/4 h plus 1/4 times 27. So the derivative is going to be negative 1/4 dh dt plus 0, because the derivative of that constant is just 0. All right, don't forget your dh dt here, because it has to be done implicitly. Okay, so now dh dt, I know what dh dt is. dh dt was given to us, so I'm going to write this in terms of dh dt. Okay. All right. Now let's simplify that. So I'm going to have 1/16 times h minus 27. Now my question is, what does this tell us about concavity? We still have an h in it. Do we know anything about h in this problem? So I go back up to the problem, and the problem did tell me something very specific. It told me that the internal temperature, that's h, is always greater than 27. It's always bigger than 27. H is always greater than 27. Therefore, this will always be positive. This is always positive since h is greater than 27. So our curve is concave up. Therefore, the tangent line falls below the curve, and our tangent line approximation must be an underestimate. So I will say that. Therefore, h of t is concave up for all h values, or for all time values, I guess. Well, h values for us too. Therefore, the tangent line approximation is an underestimate. Okay, on to part C. For t is greater than 10, an alternate model for the internal temperature of the potato is the function g that satisfies this differential equation. So this is for when time is greater than 10. Okay, g is measured in degrees Celsius and g of 0 is 91. Find an expression for g of t. And based on that model, what is the internal temperature at time 3? So here's the differential equation. Solve for g given this initial condition. This is when we get to earn a lot of points, because this is when we get to solve that differential equation. So I'm going to write the differential equation. And now we separate and integrate. Separate and integrate. So I'm going to begin by moving my g's to the left and multiplying both sides by dt. This -1 I'm just going to leave over here, so I'm just going to divide both sides by g minus 27 to the 2/3. Like that. And now we will integrate both sides. Integrate both sides. Well, this is g minus 27 to the negative 2/3, right? I'll write that down for you guys. G minus 27 to the negative 2/3. Okay, so we can do a u sub if you want, but du is just dg, so I'm just going to go ahead and treat this like a u to the negative 2/3. So raise the power by 1, but I'm going to keep it g minus 27. Raise the power by 1, and we're going to be multiplying by 3 over 1, or 3. Yes, we would have a plus c, but I'm combining it with the other constant of integration. Over here we have negative t plus c. Alright, we have integrated. So anytime after we integrate, we can plug in our point up here. I think I'm going to wait. I think I'm going to wait to do that for this one. I'm going to divide both sides by the 3. So I'm multiplying both sides. I'm multiplying both sides by 1/3. Okay? So we'll have g minus 27 to the 1/3 is equal to negative 1/3 t plus 1/3 times any constant is just another constant. So I'm just going to leave it c. Okay? And at this point, I might go ahead and plug in, I think I'm going to go ahead and plug in my value now. 91 minus 27 I think is going to be doable for me. So I'm going to go ahead and plug that in there. So tell AP when you do that though. Tell it, because don't just start getting some numbers here. Tell them what's making you get these numbers. So I'll have 91 minus 27 to the 1/3 is equal to 0 plus c. So c will just be 91, the cube root of 91 minus 27. 91 minus 27, let's see. Got 4, and then 8 minus 2 is 6, and we have 64 to the 1/3. The cube root of 64 is 4. So c is 4. I go back to my equation, my last equation that had a c in it, and I have g minus 27 to the 1/3 is negative 1/3 t plus 4. I'm still finding an expression for g of t, so I need to solve this for g. So I'm going to raise both sides to the power of 3. And then add 27 to both sides. And that will give me g of t. You can still just call that g and you'd be perfectly fine, because g is the same as g of t. So either way is fine. So we found the expression for g of t, and now we just want to plug in 3 for t. So g of 3 will be 27 plus negative 1/3 times 3 plus 4 cubed, and that's my safe stop spot. So we are good with that, just leaving it like that. That turned out to be 54 degrees Celsius, by the way. Okay, let's see how they scored this. Up on part A, they gave 1 point for getting the correct slope. So 1 point for this correct slope, 1 point for the tangent line, and then 1 point for the approximation. So 3 points for that. For part B, this kind of surprised me, but it was only worth 1 point. It was 1 point underestimate with reason. Surprised me that thing was only worth 1 point. I really thought that they were going to give me a point just for finding the second derivative. But they didn't. Okay. Part C did not surprise me. This was worth 5 points. So 1 point for separation of variables. One point for the antiderivatives. So 1 point if you separated. The next point was for your 2 antiderivatives. Okay. 1 point for the, here's what they wrote, constant of integration. That's your plus C. And uses initial condition. Okay. Which we did. We used that initial condition. 1 point for the equation involving g and t, and then 1 point for g of t and g of 3. So those were your 5 points. So again, 1 point for separating, 1 point for your antiderivatives. Here were our 2 antiderivatives. 1 point for the constant of integration and uses the initial condition. 1 point for your equation involving just g and t. So that would be like right here. That's where that was my equation just involving g and t. And then 1 point for solving for g of t and finding g of 3. As a side note, if you do not separate your variables, you got 0 out of these 5 points. They didn't care what you did after that. You could have done everything right after that. If you did not separate, you did not get any points for this. And max 2 out of 5 if no plus C. So if you did not put plus C here, at most you would have gotten 2 out of the 5 possible points here, no matter what you did over here. Okay? So be sure you do those things. All right. Next up, I'd like to take a look at 2015. So turn to 2015. It's another differential equation problem, but this one is a little bit more straightforward. There's not a story like a boiled potato or anything. It's just, here's a differential equation. And On part A, it says, on the axes provided, sketch a slope field for the given differential equation at the 6 points indicated. So here are the 6 points indicated. Notice that there are no points on the x-axis, so we don't have to do any slope field there. I'm going to get a straight edge. You can use any straight edge. I would have a straight edge handy when you're taking your AP exam. You can use your school ID, or I guess you could have a little ruler. I'm not sure, but anyway, you can always use your school ID. But it's nice to have a straight edge for these. All right. Let's see. So we're going to sketch the slope field. So I'm going to do this a real long way. These are things I usually just do in my head, but to show you what I'm doing, I'm going to do it the long way. So I'm going to go to a point. I think I'm going to start up here with the point 0, 1. So I'm finding the slope at 0, 1, and then that'll be giving my slope right here. So I'm putting 0 in for x and 1 in for y. So that gives me a -1. So this slope is -1. So I come over here and I'm going to draw a little -1 slope. So I'm going to line up. I'm lining up that point with this point because that's down 1 over 1. And just a little line segment. And then I go to another point. Let's go to 0, 2. At 0, 2, we'll have 0 in for x still, and now we have 2 in for y, so that will be -2. So again, I'm going to line up this point with down 2 over 1. So I'm lining my straight edge, I'm going to line up that point with the point 1, 0. Like that. And another point, let's do 0, -1. So 0 in for x, -1 in for y, so our slope is 1. So I'm going to line it up like this. There's my +1 slope. And we keep on going. Let's go to the point 1, 1. 1, 1, I have 2 times 1 minus 1. That's 1. So that slope is +1. I really suggest you use a pencil on these because it's really easy to make a mistake and you don't want to have a wrong slope on your little axes here. Let's go to the point 1, 2. So that will be 2 times 1 minus 2, and that is 0. So that is a 0 slope. And then one more, the point 1, -1. 2 times 1 minus a -1. Excuse me, that's the point 3. 3 over 1. So from this point, the slope will be up 3 over 1. So up 3 over 1, I'm going to kind of eyeball this about right there. About right there. +3 slope. Okay. And like I told you when we were doing this unit, they're not going to get out a little straight edge and measure and make sure it's exactly right, but you want to be really close, okay? So get it as close as you can. I know from grading these, when we took your test and when I've scored tests over the years, that it's really obvious if somebody did not know the slope. So even if you didn't write anything down, and you're not going to be graded at all on this stuff, not at all. We are only looking at your slopes, okay? So, but it's still very obvious when there's something off, okay? All right, find the second derivative of y with respect to x in terms of x and y, and then determine the concavity of solution curves in quadrant 2. So here is our dy dx, and we want to find the second derivative, so we're going to take the derivative of both sides with respect to x. With respect to x. So the second derivative with respect to x will be, okay, the derivative of 2x with respect to x is just 2. The derivative of negative y with respect to x is negative 1 dy dx. But we know what dy, we have to write it in terms of x and y, so in place of dy dx, I'm going to put what dy dx is, 2x minus y. So the second derivative is 2 minus 2x minus y. So I found the second derivative in terms of x and y. Okay? All right, now we want to determine the concavity for all solution curves given for the given differential equation in quadrant 2. Well, in quadrant 2, x, in quadrant 2 over here, x is negative and y is positive. So dy, the second derivative, which is 2 minus 2x plus y, if x is always negative and y is always positive, the second derivative will always be positive in quadrant 2. Therefore, all solution curves in quadrant 2 will be concave up. Make sense? I think so. Okay, let's see. Let y equals f of x be the particular solution to the differential equation, with f of 2 is 3. Does f have a relative min, relative max, or neither at x equals 2? All right, they are not asking us to find the particular solution. They're saying let this be a particular solution, the particular solution with this initial condition. And then they're asking us something about that. And while I'm thinking about it, for this particular differential equation, we cannot separate this. Because of this minus y, when we separate, remember we need a function of y, dy, is equal to some function of x, dx. That's separating. These have to be multiplied. If we add y to the other side, we're not going to be able to get it in this form. So it's impossible to separate this. When you take differential equations in college, you will find other ways to solve this. But for us, it's not separable, so we do not solve these kinds. But we can still use the information about it, about a solution. So does this particular solution have a relative min, max, or neither at x equals 2? Well, anytime I'm dealing with a relative min or max, especially when I've just found the second derivative, I will use the second derivative tests. So I'm going to find, okay, what is happening, what is the first derivative? What is the first derivative at x equals 2 and y equals 3? That's that point, right? So I'm going to plug in 2 for x and 3 for y. And I get 2 times 2 minus 3. This isn't even 0. This is equal to 1, not 0. So we don't even have a critical point here. So our answer is going to be neither. Therefore, f has neither a relative min nor a relative max at x equals 2. All right, then in part D, find the values of the constants m and b for which y equals mx plus b is a solution to the differential equation. All right, so we want this to be a solution. We want that to be a solution to our differential equation. Our differential equation is this. So it seems to me like I should go ahead and find dy dx here. So dy dx, I'm taking the derivative of both sides with respect to x. So the derivative over here is just m. dy dx is just m here. So I'm going to put m in for dy dx over here. And now I'm going to solve that for y. So I'm bringing y over to this side. I'm going to subtract m on both sides. And now when I look at this, this is in the form y equals mx plus b. This is in the form y equals mx plus b, where m is 2 and b is negative m. Therefore, b is negative 2. And that's it. I found the values of m and b for which that is a solution to our differential equation. Let's look at how this was scored. For part A, these slopes, they gave 1 point for the slopes where x equals 0, and 1 point for the slopes where x is equal to 1. So that tells me if these were all correct, we get 1 point. If these are all correct, we get this point. If one of these is wrong, we did not get that point. That's how I interpret that. In part B, they gave 1 point for finding the second derivative, and 1 point for concave up with reason. 2 points. Part C was also worth 2 points. 1 point for considers dy dx when at the point 2, 3, and 1 point for the conclusion with justification. Our justification was written right here. Okay, and then this part D was actually worth 3 points. 1 point for taking the derivative with respect to x of your mx plus b. That's what we did right here. And getting m. 1 point for setting up this equation, putting m in for that equation, and then 1 point for your answer. So they definitely need to see all of that. If you just throw down an answer without supporting it, you'll get none of these 3, not even the answer point. Okay, next up I'd like to do the problem from 2012, the one from 2012. So turn to that one. This may or may not look familiar to you. This was on one of our tests, or part of it was on one of our tests. Maybe the whole thing was on our differential equations test, but this was from 2012, and I kind of like it. It's the baby bird problem. It says the rate at which a baby bird gains weight. The rate at which it gains weight is proportional to the difference between its adult weight and its current weight. At time t equals 0, when the bird is first weighed, it weighs 20 grams. If b of t is the weight of the bird in grams at time t days after its first weight, then they give us this differential equation. So b is the weight of the bird. Here's the rate the weight is changing. So this is the rate equation. So that's what they were describing in that first sentence. In the second sentence, at time 0, the weight is 20. They're telling us B of 0 is 20. So they give us a differential equation, and here is the initial condition. Okay? All right, let y equals B of t be the solution to the differential equation above with initial condition B of 0 is 20. Part A. Is the bird gaining weight faster when it weighs 40 grams or when it weighs 20 grams? Is the bird gaining weight faster? That sounds like we're comparing weight. We're comparing rates of weights. We're comparing the two rates. So I need to find the rate when the bird weighs, that's our B value, when the bird weighs 40 grams, and I'm going to find the rate when the bird weighs 70 grams. And we're going to compare those, see which one is bigger. So I'm just plugging in 40 for B right here. This will be 1/5 times 100 minus 40, which is 1/5 of 60, which is 12. Okay? And for when B is 70, we'll have 1/5 100 minus 70, which is 1/5 of 30, which is 6. Let's see, I'm looking for my units just to make this make sense. The weight is in grams and the time is in days. So this is grams per day. Grams per day. We don't have to write that, but that's what it is. 12 grams per day versus 6 grams per day. So the baby bird is gaining weight faster when it weighs 40 grams. So the bird is gaining weight faster when it weighs 40 grams. Okay? So when you're doing these problems, you guys, try to make it make sense to you. Make things more obvious, the approach to take. Okay, next up, find the second derivative in terms of B. So here's our first derivative. We want to find the second derivative, so we're going to take the derivative of both sides with respect to t. With respect to t. I write that so that if there's a b over here or a y or whatever, you know to use implicit differentiation, okay, over here. So this will be the second derivative of b with respect to t. And this will be, all right, this will be 1/5 of 100. The derivative of that is just 0. And then we'll have the derivative of 1/5 times negative b. And that derivative is negative 1/5 dB dt. We need to write it in terms of b, so negative 1/5, and dB dt is 1/5 times 100 minus b. Okay? All right, so there's our second derivative. Now we need to use it to explain why the graph of b cannot be this graph. Okay, well, let's take a look at this. I'm going to simplify this a little bit. This would be negative 1/25 times 100 minus b, right? Okay. So this would be negative 4 plus 1/25 of b. Okay. All right. So let's see. Actually, I think I'm gonna leave it in that first form because now I see what I'm going to do. Okay. The lowest that b can be, is 20. and then because it only is going to gain weight, right? So B at the minimum is 20, right? And then it goes up from there. So will it ever be greater than 100? No, because of how this was explained to us. This is difference. It's the difference between its adult weight and its current weight, right? So B is between 20 and 100. So this piece is always positive. And so negative 1/25 times a positive. So the second derivative is always negative. Therefore, B is concave down for all values of B. Therefore, this cannot be the graph. Because this graph is concave up some of the times. Okay. A little bit wordy. I don't like to get wordy. I always feel a little bit, like I don't want to say something wrong when I tend to get wordy. So anyway, just make it make sense. All right. Last step. Use separation of variables. How nice of them to tell us what to do. Use separation of variables to find B of t, the particular solution of the differential equation with initial condition B of 0 is 20. So this is our chance to get a lot of points. So I'm going to do this and make sure we write down all of the steps so that I can get all of my credit. All right. I'm going to separate. So I'm going to divide both sides by 100 minus b. I'm leaving the 1/5 here. Do not multiply this out, you guys, because then you're not going to be able to bring b over unless you take everything over. And it's okay to take everything over, but it's easier just to divide by 100 minus b. So I'm dividing both sides by 100 minus b. db is still here, and then I have the 1/5 dt on the other side. And now I am integrating both sides. All right, the integral over here. Well, the integral of this side, this is a natural log because the derivative though is going to, if I let u be the bottom, du would be a -1, right? So I need to undo that negative, right? So it's going to be a negative ln absolute value of u, which is 100 minus b. Don't forget that negative, because remember, you're getting a point for the antiderivatives. So make sure you have that negative there, or you're going to lose that point. Over here, we'll have 1/5 t plus c. Okay, I'm plugging in this. I've integrated, so it makes me go and look at my initial condition. I don't want to put that in yet. I'm going to be left with this natural log for c. I'm going to just not do it yet, quite yet. So I'm going to multiply both sides by a -1. A -1 times c is just another constant, so I'm going to leave that a plus c. And now I'm taking e to both sides, And when you take e to both sides, you can lose that absolute value because the value of this constant is going to determine the positive or the negativeness of it. So this is going to be e to that exponent, which will be another constant, e to the -1/5 t. And if you do not remember why that works, ask me in tutoring. Okay? All right. Now this looks like a much better place to plug in my point. So I'm going to plug in b of 0 is 20. So 20 goes in for B, and I'll have 80 is equal to CE to the 0, which is 1. So C is just 80, and my equation is 100 minus B is 80 e to the negative 1/5 t. And now we just have to solve that for B. So B will be 100 minus 80 e to the negative 1/5 t. And if you want to call it B of t, you can, or you can just leave it B. Either way is fine. They didn't ask us to use it, so we'll just stop there. Okay, let's take a look at how this was scored. In part A, they gave 1 point for uses dB dt, 1 point for that, and 1 point for your answer with reason. Okay. In part B, they gave 1 point for finding the second derivative correctly, and 1 point for your explanation. Pretend I spelled that right. Explanation. Okay. All right. In this last part, this was worth 5 points. They gave 1 point for separation of variables. So 1 point for this step, separating correctly. 1 point for the antiderivatives. So 1 point for both of these being correct. 1 point for the constant of integration. So 1 point for that this time. Another point for uses initial condition. So 1 point for uses the initial condition, and then 1 point for solves for B. 5 points. So 1 point for solves for B. Okay, once again, they made a notation. Maximum 2 out of 5 points if no constant of integration. So if no plus C. So if you did not do this plus C, they didn't even give you any of this. At most, you would have gotten these 2 points. And another note that they wrote, 0 out of 5 if no separation of variables. So if you did not separate, you didn't get anything from this. Okay? All right. That's it. Now it's your turn to try some of these. Remember to sometimes the solving for the differential equation, solving for this particular solution, that's something that we do over and over again in these problems. It's very common. Finding a second derivative is a very common thing. But using the second derivative or using the first derivative to answer a specific question, there's no way I could possibly prepare you for everything that they might ask. So the only way to get good at this is to work lots of problems. So try your hand at it, see how you do, and I will see you in tutoring.